Hello. In this section, I will talk about the autonomous differential equations. So let's see. I have the definition first. An autonomous differential equation has the form dy dx equals to f of y. And we may notice this equation doesn't explicitly involve independent variable x, only depends on the y-dependent variable. So that's the form of the autonomous differential equation. And these are some examples, and we may notice only y prime, which is of course dy dx, equals to y squared minus y squared minus y minus 2, tangent y, interesting, and y minus 4 quantity squared. Okay, that's the examples. Okay, now what we have to do, we have to look at a certain solution of the autonomous differential equation. And this is equilibrium solution. That means let's see what equilibrium solution means. Equilibrium solution of a differential equation, it's happening when the rate of change of the dependent variable is zero. Basically, when the derivative is zero, and we may see this, dy dx equals to zero. Now, for the autonomous differential equation, because we will just talk about this, it also happened that this is equivalent because we know the autonomous differential equation dy dx equals to a function of y. That means if the derivative is zero, then respectively function y, f of y equals to zero. Now, if the derivative is zero, function must be constant. That means that's actually the constant solutions. Equilibrium solution is a constant function. And if it's constant, the equilibrium solution will appear as a horizontal line because graph of the constant function is a horizontal line, constant function. Okay, that means let's see. Also, what is important? These solutions represent a certain state of balance or stability with the entire differential equation model. And what we will do, we will try to define this stability because this solution could be stable, could be unstable, or could be semi-stable. Okay? So for instance, let's maybe really quickly, before we start looking at all of these 5 examples that we just saw on the first slide, let's actually take the first one really quick, dy dx equals to y. We, of course, know the solution. Yes, we know the solution is beautiful exponential function. And now, when this function is constant, we know that the exponential form e to the x is never actually zero and never even negative. That means the only way that this is constant is when the constant c is zero. Then this leads to the y equals to zero. Horizontal line. That means y equals to zero is actually an equilibrium solution. And we may even notice dy dx equals to zero if the right-hand side equals to zero. That's what this means. This is the equilibrium solution because derivative is zero. And based on because we do have nice explicit solution. We may notice if the constant is positive, we will have let's say 1 e to the x exponential growth, or maybe 2 e to the x3. That means this will be the potential solution, the family of the solution. If c is -1, negative e to the x, -1, -2 e to the x, and so on. Okay, that's mean we will, in a minute, we will name this type of solution because that's equilibrium. Y equals to 0 is the equilibrium. Horizontal line, this is also a solution. And the other one behaving like this. Okay, and let's name it what this means with respect to the stability. Before we start, let's properly define this. That means I have a nice definition, but we will do examples and I know that we will understand. I also have a nice description. You may pause the video and read all of those. And I have even more description. Okay, but let's come back to the definition. An equilibrium solution, Y star, is stable if a solution Y for close enough initial values Y0 to Y star 0 satisfies that limit. That means what this means. As X is approaching infinity, all of the solutions are approaching the equilibrium solution. They tending to get closer and closer. It's like a horizontal asymptote. We remember, in order to find the horizontal asymptote, we were computing limit at infinity. That means this equilibrium solution must be like an asymptote. All of the other solutions, they have to tend to approach equilibrium solution. If they diverge away from the equilibrium solution, then this solution is unstable. And let's come back really quickly. We may see this one is going away. That means that horizontal line is not really the limit. It's not really a horizontal asymptote. And that means this will be unstable. This will be unstable equilibrium solution. Okay, we have the first one. Okay, but let's see how we can determine, even if we don't have explicit function, explicit solution. Okay, that means now I just type this definition a little bit like different. We can see the solution A, the equilibrium solution, is stable solution if starts near A, tends towards A. Yeah? As t approaches infinity, t is independent variable. Unstable if leaves, which means deviates away from that horizontal line. And we also actually have semi-stable solution because it can start near, which means it will approach A, but then it will leave away, it will go away. We will see, we will do all of these examples. Now, what is helpful? Helpful is something that is called phase line. Phase line is a diagram that will actually show us this stability. And what it is kind of like a first derivative test, or we can also call like the sign analysis test. And we remember this from rank 1. Okay, we know everything. Let's look at these 5 examples really quickly. Yeah, you can of course do on your own, or you can work along with me. That means we have to find this equilibrium solution of this autonomous differential equation and then determine the stability. We actually did this one, but let's do it with the phase line. That means equilibrium solution is if the derivative equals to 0. Derivative equals to 0 if and only if, for this equation, the right-hand side equals to 0 and nothing to solve. Y equals to 0. Now, drawing a phase line means that I will draw horizontal line, yeah, because we're just testing the sign. This is equilibrium solution, and now because it's just that quantity, just that y. That means on the right-hand side, the right-hand side at 0, y is positive. Yes, we will have positive value. And on the left-hand side at 0, it will be negative. And we remember if, and this is also, because I can also say this is also the derivative. Derivative sign, first derivative test. If the first derivative is positive, function is increasing. If it's negative, it is decreasing. Yeah, that's just the recall. But how we can, because this is actually our phase line. We have to look at this like behavior. And now, please remember, if it's decreasing, like negative, it will always go to the left-hand side. That phase line will indicate the arrows to the left-hand side, away from the equilibrium solution. If it's plus, increasing, if we see the plus, always the arrow will be point to the right-hand side. Always to the right-hand side. That means minus means that we're drawing an arrow to the left. Right-hand side means plus. I mean, other way. Plus means the right-hand side. Okay, that means the arrows actually are pointing away from the equilibrium solution. This is unstable. And we know this unstable equilibrium solution, y equals to 0. If we will draw this as a solution, that's when we remember this is the equilibrium solution, 0, and below the x-axis is decreasing, and we knew because we know the solution, decreasing. Above is increasing, and we can see they tend to go away. Yes, relatively close to this, but they go as x is approaching infinity, the limit is not that equilibrium solution, it's going actually away. This is unstable equilibrium solution. Beautiful. And I have this graph. We can nicely see the slope field and it's going away, unstable. Okay, example number 2. The same thing, find the equilibrium and determine the stability. Okay, equilibrium solution is when y prime equals to 0. Derivative is 0. If and only if y squared minus y equals to 0, because that's on the right-hand side. Okay, let's factor out. We're solving like a quadratic equation. And now y is 0 or y is 1. We have two equilibrium solutions. Let's draw a phase line, 0 and 1, and let's test. If y, for instance, is like 2, 3, 4, that entire product, maybe I can use different color. Okay, let's say 2, well, we have to test the sign, because this is that derivative. 2 times 2 minus 1 is positive. Now, when I substitute maybe test value between 0 and 1, let's say 1/2, 1/2 times 1/2 minus 1 is negative. And let's take -1, -1 times -1 minus 1, it will be negative times -2, positive. Okay, now let's draw the arrows. If it's plus, we know that it's always pointing to the right-hand side. If it's minus, it's always to the left-hand side, pointing. And that's the arrows. And if it's plus, it's pointing to the right-hand side. And of course, we know that this means increasing, decreasing, increasing. Okay, and we now see 0 is stable. That means this is stable equilibrium solution. 1 is actually unstable. The solution goes away, the arrows goes away. And if I will draw this, how can we draw? Let's say this is x independent, this is y, 0 and 1. Okay, 0 and 1. And below 0, function is increasing. That means the solution will look like this. When is above 0 is actually something like this. Oh, no, a little bit too slopey, because it has to go like this. Okay, like this. Okay, that we can see, beautiful, 0. The limit is 0 of the function. I'm referring to this more formal definition. And for the values greater than 1, if y is greater than 1, is increasing. That means it's behaving like this. And then at 1, equilibrium solution 1, we may notice is actually unstable, because the solution goes away. Beautiful. And that's the graph. I don't have the solution. You may solve. It's a separable differential equation, and it's easy to solve. Okay, away, and it's tending to approach as x approaches infinity. Okay, unstable, stable. Good. Okay, 3 more. Another one. Let's speed up. Equilibrium solution is when the derivative is 0. Derivative is 0 if this quadratic expression is 0. We may try to factor out y, 1 and 2, negative, negative, positive. Okay, that means y equals to -1 one of the equilibrium solution, and y equals to 2. Okay, let's put the phase line, negative 1 and 2. When we test, let's see again, when I substitute 3 to that form, because this is the derivative, 3 plus 1, 3 minus 2, positive. When we substitute 0, 1 times negative 2, negative. And when we substitute negative 2, both negative multiplying positive. Okay, and again, positive means that for the phase line, the arrow is pointing to the right. Negative means to the left, and positive means to the right. Okay, similar situation to the example number 2. And this is for the function increasing, decreasing, increasing, because derivative are positive, negative, positive, respectively. Okay, and now we can see, we can call negative 1 stable because arrows are pointing towards, and 2 is unstable. Equilibrium solution, of course. And when we draw, let's see, negative 1, that's x, that's y, negative 1 and 2. It means similar, yes, really similar. Increasing below negative 1, that means increasing towards, yes, approaching. Decreasing, that means it will be something like this, yeah, crazy equation. And then increasing. Actually, that's almost the same like example number 2. That means it's a good practice. And I think another example, oh, tangent. Tangent of y. It's a little bit, yes, crazy, but let's do it. Y prime equals to tangent of y. That means equilibrium solution is if the derivative equals to 0, derivative equals to 0, if and only if tan of y equals to 0. And now we know when the tangent equals to 0. Tangent for what angle equals to 0? For 0, pi, 2 pi, 3 pi, and so on. Let's say n pi. N is a positive. I mean, n is an integer, also negative. Okay, but we also have a little bit of problem between, because that means that we will draw this in a minute. We also have to be really careful, and we can just draw graph of the tangent, because tangent of y is also undefined at some point. And what are the points? Tangent is undefined at vertical asymptotes. Pi over 2, 3 pi over 2, 5 pi over 2, and so on, n pi over 2. Okay? I mean, when we will draw maybe the graph of tangent, y, let's say this is, this will be tangent of y, that we do have an asymptote. Maybe I don't, let's keep this, let's treat this as a baseline. Okay, that means that's the asymptote, negative pi over 2, pi over 2, 3 pi over 2, and so on. And that's 0, that's pi, that's 3 pi, and so on. And tangent looks like this, right? That's the tangent. That's we will know the sign. Tangent at 0 from the left-hand side is negative. On the right-hand side is positive. And again, negative, positive. Below the x-axis, above the x-axis. That's we may notice all of these solutions, because that's the equilibrium solutions. They are unstable. Unstable because the arrows will be left-hand side away, right-hand side away, left-hand side, that's the arrow, and the right-hand side, left-hand side, and the right-hand side. That means all of them are unstable. Okay. Also, these points, slope is undefined. If the slope is slope is undefined, I mean derivative is undefined. Derivative is undefined. Then slope is actually vertical. slope vertical. Remember, because if the slope is undefined, slope is actually vertical. That's we have interesting situation. Oh, I don't have room to draw. I mean, I have the graph, but let's maybe try. Yeah, let's don't look at the graph. That's mean what we will do. Let's try maybe to see how the solution looks like. Yeah, that means this is the differential equation, autonomous differential equation. And we know 0 is an equilibrium solution. Pi is the equilibrium solution, and maybe one more. 2 pi negative pi is the equilibrium solution, horizontal line. Negative 2 pi. But in the middle, we have this undefined points, pi over 2, 3 pi over 2, the vertical, negative pi over 2, negative 3 pi over 2. And now let's see, when we look at this, decreasing, increasing. That means 0 for values less than 0, yes? This is less than 0, is decreasing. That's we will have decreasing and vertical and increasing, something like, but this is vertical. It's like at that point is vertical. And now on the above, for the values greater than 0, is increasing vertical and this. Yeah, that's we can see it's definitely, and again, vertical. It's something like this, something like this. But at these points are vertical slopes. Okay, interesting solution. And now, if you've tried this, let's look at this. Yes, it's like vertical and this, vertical. That means all of the solutions are actually unstable. Okay, and let's just really quickly do the last one. Okay, the last one. Equilibrium solution and stability. Equilibrium solution is if the derivative equals to 0, derivative equals to 0 if this is 0, then right-hand side. This is 0 if y equals to 4. Okay, and now let's see what's happened. Phase line 4. When I substitute like 5 minus 4, it's positive squared positive. When I substitute 3 minus 4 is negative 1, but when we square, it's also positive. I think this is interesting because to the right. If it's plus, it's always to the right-hand side. That means this one solution is, let me do this, it's tending to approach 4 and then it's going away. That means this is semi-stable. Let's see how this looks like. If this is 4, then the solution will go increasing because it's increasing. Okay, and then it's also increasing. Yeah, that means this we will call semi-stable solution. Okay, semi-stable solution. And I have actually, we can see this, and then away. Okay, that's mean we went through all of these examples. I hope now you understand what is autonomous differential equation and what is the equilibrium solution and then stability of the equilibrium solutions. Thank you. Thank you.